Hello everyone, myself Tabish Ahmed, final year BTech student from Electronics Engineering at Zakir Hussain College of Engineering Technology, Aligarh Muslim University. Today I am going to explain the complete structure and the flow of a priority encoder from a schematic to the GDS2 file on the Cadence Virtuoso. So first of all, I would like to gratefully acknowledge the support of Chips to Startup program by the Government of India for given to the Aligarh Muslim University, due to which we can use the industry standard tools like Cadence Virtuoso in our university. So today we are going to design a priority encoder on the Cadence Virtuoso using the Chips to Startup help on the server of Aligarh Muslim University. So first of all, as you can see on the screen, we are going to make a new folder named as whatever the project we are going to make. So today we are going to make a priority encoder. So we will make a project named encoder. So it was already open. So we are going to start it from the beginning. So first of all, the new folder has been made. Then we will open the folder. Now we will open the terminal inside the folder and write these commands to start the Cadence Virtuoso software. Now as you can see, the software is opening. Now we will make a new library named as encoder, in which we will do all our work. So we will give the name encoder. Then we will use this option attached to existing technology. Press OK. Now we will use the technology file that we are using. So we will be using 45 nanometer technology. Now the folder is ready. Now we will make a new cell view, in which we will make a cell named as encoder that will be a schematic type. We press OK. Here the schematic window came, in which we have to make the schematic of a priority encoder. So as you can see on the screen, we have a workspace and we have so many options at the top. So what we need in a priority encoder is that we need some PMOS and we need some NMOS. So we will add the instances in library. We will go to the GPDK 45 nanometer technology, and we will select NMOS, 4 terminal NMOS, and we will hide these options. So here it is. We will place this NMOS in the workspace. Uh, we will place two NMOS, and now we will place no, it will be PMOS. Yeah, we will take now PMOS from the instances from the same GPDK045 file to remain in the same technology. We will give this twice the width of the NMOS, as in digital design we keep the width of the PMOS twice. Now we will make the connections. By pressing the key W, we can make the wires between these NMOS and PMOS terminals. So we press the key W and then we will connect these terminals. Here the body should be connected to the source. So we are connecting this body to the source, this body to the source, and the remaining terminals. And we know that the NMOS source will be connected to the ground. So we will extend a wire that will later be connected to the ground. We will extend some wires at the source of the PMOS also. We will extend this output terminal wire. We will extend some wires for the gate terminal also. So basically we are making a transistor level schematic. Here we will extend some gate terminal wires. So basically this is a structure of a NOR gate that have two PMOS in the PUN and two NMOS in the PDN. Now we will create some pins, as you can see in the video. We will create some pins named VDD and ground. So this VDD pin will be connected at the top and the ground pin will be connected at the bottom. We are rotating this pin by clicking the R button at the keyboard. Now we will connect this pin with the wire to the terminal. Yeah. Now what we will do is we need two NOR gates for the priority encoder. So basically currently we have this NOR gate, but in the priority encoder we need a OR gate. So what we will do is we will make a inverter that is a NOT gate in front of this NOR gate, so that the overall gate will be a OR gate. In priority encoder we know that we require three OR gates, one AND gate and a one inverter. So making a OR gate from a NOR gate, we need a NOT gate cascaded to the NOR gate. So that's what we are doing. We are connecting a NOT gate in front of this NOR gate. So the overall function will be a OR. Now similarly we will connect the connections with the W key, source to the body, source and body, and we will similarly create some pins named VDD and ground. We will extend the output wire. We will create the pin VDD space ground. Now I have selected this complete OR gate and I will make a copy of it, and then we will continue making these circuit diagram similar to that way. I have fast forwarded this video so that we can make this quickly. We will make the remaining connections of the remaining gates. We need a 4 input NOR gate also, so we are making here a 4 input NOR gate. Connections are being made similar way as we have shown for the single NOR gate. This will become a 4 input OR gate. Now what we need is we will need a AND gate. So for that we need two PMOS in the PUN and two NMOS in the PDN. We will make the respective connections. Since it is a NAND gate, so we will add an inverter so that it will become an AND gate. And in the priority encoder circuit we have this inverter also in the initial. So now we will make the interconnection between the gates as in the schematic of a priority encoder. Okay, so now we have got a complete connections for the priority encoder. Now we will create some pins as the input pins and the output pins of this complete priority encoder. So we'll create pins named okay, let it be V in 1, V in 2 and V in 3. And V in 4. So we'll place these pins at the input points here, here. Now we will create some pins for the output points named Vout1, Vout2, Vout3. So basically these Vout1 and Vout2 are the output of the encoder, and the Vout3 is basically indicator. So we will place these pins. Okay, we will save this. Here we can see in the .log that there is no errors in the schematic, so we can proceed with the further steps. So now we will save and check, and here you can see schematic check complete with no errors. We will minimize this window. Now we will create a symbol, cell view from cell view named encoder. Now we will make a symbol for this complete encoder. So whatever be the left pins, we will place it there, that are the input pins. The right pins will be the output pins. The top pin is VDD, and a bottom pin will be named as ground, GND. Okay, so we will press OK. Here you can see and automatically a symbol is generated in which 4 inputs are at the left, 3 outputs at the right, VDD at top, ground at the bottom. We will name it as encoder, and yeah, now we can save it. And now whenever we want to need this whenever we want to call this encoder, we will call this symbol instead of this complete schematic. Okay, so this is the complete schematic flow. Now here you can see encoder schematic saved, no errors. We will open cell view. Here you can see cell named encoder, view schematic. Now what we need to do is we need to call that symbol and make a test bench. Like we have to put some voltages on it so to see its output. So for that we will make a test bench named encoder TB, in which what we will do is as we have instantiated some PMOS NMOS in the previous schematic, we will call the complete symbol of the priority encoder that we have made, that is inside the encoder, this encoder file. We have encoder, you can see the symbol will present. So we will call this symbol in the test bench, and we will add the voltages at the input, some pulse voltages, and we will add the VDD voltage, the ground value, and then we can see its outputs. Okay, so we will add instance. We will go to the analog library in which we have to call the ground symbol that we have to attach at the ground, that is okay, firstly we will what we will do is VDC. In VDC, it is generally a voltage, DC voltage. We will add this like positive terminal to the VDD of the symbol and negative terminal to the ground. Again, we will browse and go to the analog library, in which we will call this ground symbol. As there are four inputs, four voltages will be there. Each voltage will have a ground terminal, so we have placed these grounds. Now we again add some V pulse that will have pulse value in it. So in it we will give a 0 to a zero point 0.9 voltage, a high as a 0.9 value of 1 microsecond pulse. Next we will add a voltage pulse of same voltages and a period of 8 microsecond, pulse width of 1 microsecond, and we will, what we will do is we will do the pulse width twice as of previous one. So at 2 microseconds, third will be of 4 microseconds, 3 microseconds, okay, and next it will be of 4 microseconds. So basically we have different pulse width pulses which we will give it the input of the encoder, and we will see output accordingly. If it matches as the functionality of a priority encoder, then yeah, our schematic is correct. So we will do the connections, and similar way W for the wire, and you can move it by simply dragging the symbols. So we will add some wires, we will add the VDD, we will add some wires as the output extensions. Now we will create pins at the output. Remember to keep these pins as uh, right sided, because it's a output pin, so direction should be output. Okay, in the window direction should be output, and at the input side the direction should be input. Yeah, so we'll add these at the wires. Now our encoder test bench is ready. What we will do is we will run its transient analysis, in which we will run these pulses with time domain, in time domain. So here you can say no errors. Now what we will do is we will run the transient analysis. Yeah. So in launch we will do the ADEL. In this window what we will do is just let it load. Okay, just press the session. Okay, now what we will do is we need to add a transient analysis. What kind of analysis? Transient, because we need it with respect to the time. So we will open this ADEL in the launch. Just let it open. Yeah, in this analysis part we will add tran, in which we have a stop time of 10 microseconds, and we will apply. Okay, now in the outputs we will add to be plotted, select on design. Now we will select pins that we want to be plotted. So we need inputs to be plotted, and yeah, we will select these wires, and we need output to be plotted. So we will select these output wires. Okay, so we have added it. We will run the analysis. Here it comes, running window. Let it open. Yeah, we will separate these curves by clicking this button. Yeah, so here it is, the output. It's correct according to a priority encoder. Next we will move towards making the layout of this schematic. So what we will do, we will open the schematic, and we'll open the schematic in a window, Cadence, uh, similar way as we have opened earlier. not the test bench but the real schematic. Okay, we'll give it, then in launch, layout Excel, create new, and let it be the name encoder only. Now you can see the view is of layout type, so we will press OK. Yeah, so here it is, the layout window. You can see the schematic window, and side of it, and on the side of it we have a layout window. So it's currently empty. We will go to the connectivity, generate all from sources, and what we'll do is in this we'll do nothing but minimum separation 1, input output pins. We will need metal of width 0.06 is there, but yeah, let it be 0.01. Okay, let it be 0.12. 0.12. Okay, we will apply it. Okay, so here you can see the new NMOS and PMOS blocks are being generated according to the schematic. Okay, so schematic file is always connected to it. This box, you can see the yellow box is the outline for this complete layout. So we can expand it by clicking the S button on the keyboard, so it can expand these box. We will press, yeah, these blue boxes are the pins that we have named: V in, V out, and VDD, ground, everything. And these blocks, you can say, are the PMOS and NMOS blocks. So when we open the schematic, here you can see, okay, the session expired. La. So you can see the schematic, and you can see the corresponding layout boxes. So whenever you will press, let me fix it. Yeah, whenever you will press any PMOS or NMOS block in the layout, respective PMOS and NMOS of the circuit will glow also. So from which you can verify that which PMOS is connected to, should be connected where should be connected. So it's a great thing. You can click on any block and the respective block in the schematic will glow. Similar with the pins, if you click any pin, same. Yeah, so what I've done is I am moving all the PMOS on the upside and all the NMOS down, so that we can make a schematic, we can make a layout. Here in the place, you can what you can do is you can use the pin placement, in which you click the VDD pin, horizontal rail, and the ground pin as the horizontal rail. But as you can see, these rails are coming in the middle. It should be on the top and the bottom only. So what we can do, uh, we have to place these pin according to the symbol. In the symbol we have placed the ground at the bottom and the VDD at the top. So what we will do, we will go to the place option again. Yeah, if we want to move, it's random, but to be on the safer side, what we will do is we will place these pins according to the symbol only. So here's the schematic. You can see all the grounds. As the ground is clicked, the ground is glowing, so that pin should be at the bottom according to the symbol. So we will go to the place, pin placement, we will click as symbol. Now every pin will be placed similar to that in the symbol. We will press VDD, horizontal rail, it will be in the top, ground, horizontal rail, it will be at the bottom, similar to that in the symbol. So here it is. Now what we need to do is uh, we need to bring all the NMOS at the bottom and all the PMOS at the top, so that we can make a usual layout structure. So that's the thing we have to do now. Yeah, you can keep these windows side by side, and now when you click on the NMOS and PMOS, the respective NMOS PMOS will glow. So what we need to do is we need to place the PMOS in the single NAND together, PMOS in the single inverter together, PMOS in the single NOR together, NMOS in together, all these components together that are in the single gate. So we will do the placements by dragging these boxes. Let me show you. Yes. So you can see currently these PMOS are just randomly arranged, but we have to arrange it systematically according to the schematic. Uh, it's something like playing with the boxes and placing at the correct place. Now what you can do is just click Shift F, and you can see the colored view. And when you click on the properties of a PMOS or NMOS block, you can also show or hide its NVEL and PVEL. So when you click Control F, it will be a block view, and when you click the Shift F, you will get a colored view, like what you generally see, like polysilicon, the NVEL, the active region, everything you can see when you press Shift F on the keyboard. So it's the look. It looks like this. You can see S at the left side, that is the source, and D on the right side, that is drain. So these two, and don't forget to press E on the keyboard and set the grid controls to 0.01, so that you can move these blocks precisely instead of like not unprecise. Just put it to 0.01, it's enough for a precise movement. So press E for coming to this window. Yeah. Now what we need to do is we need to connect the source of the right one PMOS to the drain of the left PMOS, as in the schematic you can see. So what we will do, we will overlap these two parts, the source and the drain of these PMOSs. We will overlap them so that they get connected, but this may give an error. So we can go further in this layout structure, and we can remove those errors. But currently what we will do is we will bring these PMOSs together and overlap them so that they get connected. And similar, as I said, you go to the properties, detach, top tap, and OK. So here now you can see the P well for this N well for this PMOS. You can see this box coming upside of this PMOS, that is the N well. So here it is. Now you have to go to the create and shape rectangular, or you can only press the R key. Now you can select the anvil and extend this box for the complete PMOS, complete 2 PMOS. Here it is. It's this structure is ready. Now we have to do the same thing for the NMOS. We will align them in front of each other, and then we will bring and overlap the two parts as shown in the structure. We need to connect both the drains together. So just a second. Yeah, so both the drains are connected now, and the source, we will select it. We will go to the properties, body type detach, bottom tap, OK. So here it comes, the P well for this NMOS. So for this, what we will do is we will again create a box for the P well for this NMOS. that is named as PW dummy. So we will search for PW dummy in this option, uh, PW dummy. Scroll it, scroll it. Yeah, PW dummy. We will create, press the R key on the keyboard, and you can make the box now. Okay, that's it. You can create shape rectangle and make this rectangle, extend it. Okay, so here it is. Both sources to the ground and both the drains are connected together. Now this complete, in the schematic you can see it is the NOR gate. Similarly, you have to do this complete method, what we can say, this complete procedure on all the PMOS and NMOS. So let me fast forward the video and do the same thing for all. Remember to press Q or right click on the PMOS to go into the properties, then go to the body type, then make it detached, and if it is PMOS then do the top tab, if it is NMOS do the bottom tab, and then you can get this NWell and PWell for respective NMOS and PMOS. Okay, but remember this overlapping sometimes gives some errors in the layout correction checking, so we have to remove those errors later. Let me complete this structure, then we will check the errors with the help of DRC, Asura DRC, that's option. So let me complete the structure first. You not need to add this N-well and P-well for all the PMOS that are connected. You just need to place this well for the single PMOS and then use that rectangle tool to extend this to the complete structure. Okay, so as you can see, I have almost completed everything in the structure part, like in connecting the PMOS and NMOS according to the schematic. Now what we need to do is we need to connect these polysilicon lines and metal lines. So let me do it and I will show you the look, how it will look like, how it will look after completing the connections. For connection you can press the P button and continue with connecting the polysilicon lines and the metal lines. So let me open it again and let me show you. Yeah, it will look like this now after the connections. We have connected the polysilicon gates with according to the schematic. Now we will run the Asura DRC in which we have added the 45G library, and here you can see error. If there, yeah, here are 8 errors. 8 metal 1 errors, in which the first two errors are like we have not connected them yet, but these overlapping errors are coming. So what we need to do is we have to remove these overlapping errors by checking by removing this overlapping. What we will do is, here you can see a blinking yellow box with a cross in it, so it's an error. So what to do to remove, what we can do to remove it is we have to decrease this overlapping area. So what we will do is we will remove some connections and just drag this what is it? This is NMOS. Okay, so we will drag this NMOS and we will separate these two NMOSes. Just a second. Yeah, we have to drag it like this. Now they are separated. Just we have separated these two NMOS, and you can see the wires are not moving with it. So you have to reconnect the wires once you have moved the PMOS or NMOS, anything when you move it, the connection will not remain connected. You have to reconnect these things. So what we are doing now is we are overlapping the two NMOS, but not completely, just a little overlapping between the two. So here it is, a little overlapping between the two, and now we have to remove these old polysilicon connections and we have to make the new one. So we'll select firstly, yeah, so I think it will be okay now. We will select these old connections and delete it by the delete key, and this connection, this one, this one, and these metal connections are also no more valid. The above net 10 you can see. We have to resize this box also. We will remove this net 10 metal connection. It's also not valid now. Now we will make new connections. We will press P on the keyboard, so it will be a wire. Polysilicon, get connected to the polysilicon. Yeah, place it there. Okay, it's connected. Now when we will go to the metal, the same P key, the P character key will work as a metal one wire. We will place this connection. Okay, so it's connected. We have to connect the bottom connection also. This box that you can see, the green box, it is a via on which a polysilicon can be connected with a metal through it. So we have connected the polysilicon to via and then Y to metal to via, so they will be connected. And we also connect this S and D because they are no more overlapping now, so they are not connected. Now we will run the DRC, press OK, enter, OK, yes, okay. So you can see the metal one error is reduced to 7, but we have got some new errors, off-grid errors. Okay, so first one is minimum M plus plant space. So it's nothing but this little error that came due to this connection. Okay, we'll see it. Next, this net, it's still giving an error. What we can see is we have reduced the metal one error that were 8 previously, now they are 7. So this overlapping is now correct, but due to the new errors we have to correct the remaining things that are getting disturbed. So what we can do is, these lines that are indicating like purple lines on the Y2 metal, they are indicating, and this polysilicon line that is indicating the error. So what we'll do, we'll move the via right under the polysilicon, and we will remove this metal connection. We will place a straight connection of polysilicon with the via. So we will move this a little bit more due to that error we received. We will move it a little more, and yeah, I think it will be fine now. Now again we have to remove the older connections and make the new ones. So we will move the via also. Yeah, this one. Okay, connect it. We connect the poly to the via, and this metal between the source and the drain, we will remove the old one and will connect with the new connection, and then connect this via with the metal line. Yeah, I hope there will be no errors now. Asura, run drc, remember to add the technology file, and then press ok, ok, enter. Yeah, press ok. Yeah, so we have removed this off grid errors. Now we have this one error, minimum n plus active area, and what we can do is we will move it a little more, remove that old connection. We will try once again. Okay, now we will make the connections again. Yeah, so we have done these connections. Connect to the poly, to the via, connect the source and drain, and this metal line connection. Okay, this will be okay. Mm, you can see this metal line is intersecting with the Y2, so they will be interconnected. So what we will do now is, instead of placing it there, we will place the ground connection with the ground. Yeah, this one here. Now they will not intersect. Okay, coming back to our problem. I hope there will be no errors now. We'll remove this old connection, make a new connection, and yeah, We will again run the Asura, run DRC. Okay, enter. Okay, okay, yes. Let it complete. Okay, great. So we have removed that error, overlapping error. Instead of 8, we are getting now 7. So the remaining parts where the cross is coming, we have to do the same exercise on each part. So now you can see that we are getting this error in yeah, this PMOS part above this NMOS, yeah, this one. Okay, here what we will do, we will drag and reduce the overlapping area. We'll let it overlap a little bit, and now we will remove the old connections, make the new connections, and you can extend this box by clicking S on the keyboard and then clicking on edge of this box, and you can extend it. Okay, so now we have got this. We have to remove the old connections, like this here you can see the PMOS is glowing, which one it is. So you can see that you have to overlap it a little. What you have to do now is you have to remove the older connections. Yeah, and you need to flip it horizontally, because in the schematic you can see the drain is connected to the source of the glowing part. So we will connect drain and source. We will connect the new drain with the previous connection, and we have to remove this polysilicon line also. So we will press S on the keyboard and move this via. Okay, move this via. Yeah, we have to remove these old connections. We have to place new connections. No, it will not be fine because it's coming too long. So we will bring it from bottom. Yeah, here. It should not be intersected with via. So here it goes, connected. Now what we will do is we will connect the via with this polysilicon. Press P, so it will be via. Connect with polysilicon. Connect with the metal line, metal one. Yeah, now it's connected. Here it is. Now we will again check the DRC whether we have reduced the errors or not. Let us check. Great, we have reduced it. Now we will do this similar process for all the intersections, and we will get a error free layout. So let's begin the work. Drag and bring it away, reduce the overlapping part, remove the old connections, and here it's already, the drain is already connecting to the source. Just place the metal line. Yeah, so when we connect, we will remove the older one. We'll extend this metal poly, connect it with this, connect metal line. We will move it a little bit here, place the metal line. Yeah, it's connected. Net 5. Okay, let's take no risk. We will connect the metals separately, that remove the old parts and connect it fresh. Connect the fresh part. Okay, so the common drain will be connected to this via. Yeah, yeah. Okay, we will do the same thing here also. Select and drag it. Select the remaining part and drag it. As you know, all the source of the PMOS must be connected to the VDD. So we are connecting that N well of all the PMOS to the VDD and P well of all the NMOS to the ground. Okay, so we will interconnect this with metal. The polysilicon must not be too close to each other like this. So we have to remove this Y3P poly. Yeah. So what we can do is you can connect it here and move it this. Currently I'm using a mouse. So the scroll key in the mouse, if you press it and move it, then you can drag the whole schematic. So I'm moving the schematic like this. Yeah. Uh, and keep in mind that the connections should be correct according to the schematic. Otherwise, if you are having wrong connections, then there might be some errors, not in DRC but in LVS check. I will show you later, but keep in mind you should do the connection according to the schematic only. Okay, so I think it's done. We need to add the metal connections now. Yeah, we need to the error. You can see that the yellow box error is coming in the NMOS boxes also. So you have to bring a separation and reduce the overlapping area of NMOS also. Like you can run the DRC and check that there are still some errors. Like uh, there are many errors. You can see the box coming here. Yeah, this is just the metal is not connecting. That's why it's showing this error. Uh, Main error is that overlapping error we have to reduce. So what we will do, we'll check more. This we have to move this just a second. When you click on these arrows, they will show where the error is coming of the line that is highlighted in the DRC window. Okay, so you can see these overlapping errors in the PMOS also, and this NPMOS, NMOS both. So connection was not there. Like we will go back to these errors. You can see there are errors in the NMOS also. So we can reduce it by having some spaces. Yeah, what we will do is here are some grid errors. That is wire I think is not connected properly in the correct alignment. So we will delete it and we'll make new one. Also here we need to shift it a little bit more because the error was showing there. Okay, so just add it here. Let me connect the metal. Select the poly and connect the gate. Yeah, here. Remove these connections. Just drag these a little bit more. just for be sure, just to get sure that no error will come. Now we will drag these NMOS also just below the PMOS in the same alignment. You can see the white and orange line that is coming. I am checking whether it is straight or not and aligning this according to the PMOS above it. So they are aligned now. Then we will connect these poly lines. Next, we will connect these poly lines also. We will remove these old connections and make some new ones. Yeah. Next, with this one to this via, straight connection with this via, and then the last one, this one. What we'll do is we will bring the poly from this via to the gate. Yeah, so it's okay now. We will check DRC. Okay, yeah, we have some off-grid errors due to that via connection, but you can see the metal 1 errors are reduced, the middle one 3 only. So there are some errors that I have skipped because of some reasons, like first one are the off-grid errors that are very basic, that the via placement is not correct, and secondly here you can see the connecting metal lines. Yeah, no, undo. Yeah, this metal line we will delete and connect the new one, as we have moved it a little bit, so these connections are broken. So we will do this again. Make sure to connect every time when you move a PMOS or NMOS. Connected with new wire, new metal line. In NMOS also the metal lines were not connected, so that was the error. We will connect them now, and these shifted ground lines should also be removed. Old connections should be removed. We'll connect new connections. This with the left one. Just a second. This is a ground, so I think it should be flipped. This NMOS should be flipped according to the schematic. Yeah, horizontal flip. Yeah, now the drain is connected to the source and ground is connected to the ground. Okay, okay, these are correct. We will connect them. We will connect them. We will connect them. Okay. The remaining ones will be connected with the ground. Here also we need to connect the metal connections. That is, uh, according to the schematic, the drain of the last PMOS with the drain of other NMOS. Yeah, this one. Just to keep care of the alignment. The alignment should be proper. Yeah, we will move it connected with the drain. Okay, so I think the connections are correct now. This off grid error. Okay, let me correct it. Uh, what we can do is we can remove this old polysilicon line and bring this via just below this polysilicon line y2, so that it will remain in the line of this polysilicon. We can move it here and just we can rotate it, or no, no need to rotate. We just connect the metal line and we will connect the poly line. Oh, okay, let me do. Yeah, poly connections. Yeah, I hope there will be no errors now. TRC, run, enter. Okay, okay. I think there is some error in the connection. TRC is not, TRC output is not coming. Okay, okay, yes, yes, okay. So here it is. We have got only three metal one errors. And just a second. Okay, yes, yeah. So the the errors that were previously the overlapping errors only three, and this new four errors. You can see this triangular area that is coming as the error. So, oh, I think let me see it at a little close view. Okay, I think the errors of. Let me add the PW dummy as the P well for these NMOS. Again run DRC Enter, enter, enter. Okay, yes. Still the same errors. So it was not the problem of the P well. Okay, this is the problem and it is indicating this triangular region. So I think it's the problem of alignment. Yeah, it's the problem of alignment. Here there are no triangular errors. Here you can see that this PMOS and MOS is a little bit off aligned, not aligned with the other two. So what we will do is we will align it with the other two. Yeah, now they are perfectly aligned. Just a second, just move it a little bit. Move it a little bit. Yeah, now it's in alignment. Now let's check whether the error is there or not. But yeah, the old connection should be removed every time. Always remember. Now new connections will be made. This one and this one. Okay, so we'll run drc. Okay, new one single error. Okay, so as I said you, the older connection should be removed every time. So these connections were not removed. So new connections will be made. Let's check the other. Yeah, this one is also shifted. So we will make the new one here. Delete new metal connection. Yeah, now we'll drc. Okay, first let me connect these outputs also. So this V out 3 must be connected with the out terminal third. Single metal connection, I think it will be fine. We'll connect this metal with the V out 3 terminal. Now the problem is the V out 2 and the V out 1. These two are having so many metal in between the connection. So the same metal line cannot connect the input, oh, the V out 1 output pin with the connections. So what we can do is we can use a metal 2 line. Okay, so let me do it. Undo. No need for that much space. We can do the connection here also. With this connection what we need is we need to connect this V out 1 with that pin at the output. So just to press O on the keyboard so that you can select the via and then select this M to M1 via, rotate it and press it where you want to place the via. So this via is between metal 1 and metal 2. So you can connect this metal 1 with it. And a metal 2 line from this via to another via near the output. Okay, so we first have to place the via. Press O, metal 1, metal 2 via, rotate, place, and then connect it with metal 2 line. So this metal 2 line will not intersect with polysilicon or metal 1. It is at the different level, so it will not intersect with others. So we can uh, bring it over these metal 1 and poly lines. and then we will connect this with the output pin using a metal 1 connection. Yeah, so here it is. Now we have to connect the vout 2 also, so one more via will be required. Yes, where is the vout 2 line? You have to see it. uh, vout 2. What you can also check where the particular line is by clicking the wire at the schematic. Okay, so it's also the respective wires in the layout will glow. Okay, let me do it and save. Just a second. So basically, while doing so, you have to take care that whenever you move a NMOS or a PMOS, you must remove the old connections and make the new ones. It is very important to get to be protected from these errors. And secondly, uh, this connections, as I already said, you must be matched with the schematic. You have to give an overview on the layout connections, that whether they are correct or not. If they are uh, like according to the layout, if they are correct, then no DRC will error will be there. But if according to the schematic the connections are not proper, or you have connected the wrong things, then LVS error will be shown. Like I will show you the LVS error check uh, in some time, but make sure that you are making the schematic, you are making the layout according to the schematic. Okay, now just a second. Okay, so we are going to connect this V out to through via and metal to line. Yeah, we have connected this. Now we will connect this via with the out pin using the metal one. Okay, so the connections are almost ready. Now we will check for the DRC errors. Run DRC. Okay, enter. Okay, yes, enter. Okay, no DRC errors are found. So great. Now, basically, now the connections of the layout means the layout errors are not there. But when now we will run the LVS and we will check whether there are LVS errors or not. So it's running. Yep, there are some LVS errors. So it can be corrected simply by reviewing the schematic and layout. Wherever some connections are missing or you have done some wrong connections. Now I will show you the final layout structure. It will be like this. This is the final layout structure with all the connections, and we will check the final DRC and LVS errors. So I will show you run DRC. Okay, okay, yes. So the LVS errors that you were seeing previously were due to some of the connections that I have forgotten. Like I have not connected the poly connections of some of the gates. So it's just because of that. It's easy to remove the LVS errors. Now we will run the LVS again. Okay. Uh, let's see. Uh, yeah. No LVS errors. That's correct. Okay. So we will go press yes. So no DRC violations, no LVS violations. So basically our layout is ready. It's perfectly ready according to the schematic. And as we know that we have done the schematic working, so our layout will also be working. So next what we need to do is we need to add the resistances and capacitances. So for that we will go to the Quantus, setup Quantus, extraction. We will add this in the setup. Okay. We need to add the RC values to this layout. So we will do this RC, all the resistance and capacitances. We will add the reference node that is G and D, that is ground, in our layout. Make sure you will put the same name uh, here also. So be careful about it. So we will apply. Okay. Yes. Okay. So in Asura we will run the Quantus now. It's set up. Okay. Extraction RC, section type RC, reference node GND. Make sure you have giving the same name and then apply. Okay, no, there's some error. This. Okay, sorry. We have to set the rule set of RCX typical, not the default. RCX typical. Now we will apply. Okay, the Quantus progress form is appeared. It's running. Okay, it's successful. The Quantus run is successfully completed, but it's not giving the extracted file yet because okay, there is something I have forgotten. Just press OK. what you must see here is a successful completion of Qantas along with a extraction file generation. You in a command window, in the display pop-up window, you must see extracted file is generated, but here it is not showing any extracted file that is generated. So I think let me do it again. Let me close this uh, LVSD, but it's the old window. Just cut it. uh, what we are trying to do is we need to add the resistances and capacitances that come due to the layout structure, like metal lines and the detective region, silicon, everything cause the formation of resistances and capacitances. So we need to extract a file of that resistance and capacitances. So we are trying to do that. So let me try it again. Okay, the server is now down. Let me open it again. Yep, here it is. It's the layout. We are going to run Qantas. Just make sure that the DRC and LVS that you have run must be using the same GPDK libraries that you are using in the extraction of Qantas run. Like you should not be using any other library while DRC run, LVS run, and Qantas run. So make sure that here the technology is GPDK 045, so it's correct. Okay, so let's check once more. Zero LVS errors. Okay, zero LVS errors. Now we will move towards the Qantas. We will set up this. Okay, now minimize this window. We will go to the Asura, run Qantas. We have already set it up. Okay. Yeah, I think I haven't unticked the extraction HRCX file. Okay, let me show you. You must untick this enable HRCX. You must untick it. Now I have unticked it. We will press OK. Yes. And let the Qantas run. Hope we will get the extracted file now. Yeah, here you can see AV extracted file has been generated. So now we have got the generated file, we have got the layout, we have got the schematic. Now we should move towards generating the GDS file. So we'll go to the open layout, AV extracted. Okay, yeah, here you can see it's the extracted file. In this you can see small resistance and capacitances are being yeah, small resistances and capacitance symbols are shown. Shift F, yeah, this one. This is small capacitance, resistance, capacitance. These are being added. So now this is very much similar to the real life chip. which have this resistance and capacitances. Now we should move towards the GDS2 file generation. So what we will do is, just let me close these things. We will go to open, export, export stream. In this you have to add the stream file, in which you have to go to the original folder in which you are doing the things. Like in this case we were on the desktop. In the desktop you must select the folder that you are working in encoder. Okay, just save it and put some file name in it, like let it be extracted encoder file. So I'm putting this name .gds. Remember to write this extension. Save. Next, library. We already know what library we have used. We were in the no, we have to select the library in which we were working. So it was the encoder folder library that we have made for our own working space. So it includes all the cells, all the things that we have generated. Okay, so it was the encoder library in which we have to select the layout. Now the technology library will be GPDK45. Now you can see that the log file is generated. Your GDS1 is exported. Now the next step will be the import part. Okay, so let me move further. Like we have done the half of the step of generating the GDS file. Now what we will do is we will go to the file. We will press import, in which we will select the stream. And now we will select the stream file. Same thing that I have said, that GDS file that we have exported, we will now import it, and we will use the library like encoder that we've already made. Mm, yeah, so GDS lib45, we will give a name to the library, our own name. Okay, so let it be GDS lib45 tab. Now the top cell, uh, whatever we need to give the name, we will give encoder. Next we will move towards the view, that is layout. Okay, sorry for that. Just press the translate button after that process, so you can generate the GDS2 file. Then now what you can do is open and go inside the encoder. You can find that name that you have generated, like uh, GDS lib45 tab that we have given. You can see this library, and in layout you can open this file. Okay, so press OK. You can see this is the GDS2 file now. So this is the process. uh, this is the process of generating the GDS2 file. So you can see by zooming, Shift F will show you every insight of the blocks. Here it is the final look. So just to go to, yeah, this export image. You can export it as an image, so that you can save it and print or place it somewhere else. So we can give any name and save it as a image file, .png or whatever extension you need. So that's it for today. Hope you have learned something and get to know about Cadence Virtuoso design.